Alright guys, let's get going with some study guide solutions. So the very top of the first page has a test your understanding, and you have 4 objects that are moved during a 4-second interval, and we have some velocity versus time graphs. So we want to do 2 things. We want to rank them in terms of their acceleration and then displacement during that time. So when it says most forward and most backward acceleration, I see 4 blanks here. I need to have all 4 letters there. I'm ranking them from most forward acceleration to most backward acceleration. Forward acceleration for us is positive. Backward acceleration is going to be negative. So how do we go about that? Well, let's pull up our graph reference sheet. So I've got the reference sheet here, and I'm looking at a velocity versus time graph. So that means I'm going to be bound to this middle row here, and I can find these things, or these are my characteristics of the graph, and then these tell me what those actually mean for my velocity versus time graph. So if I'm looking for acceleration, well, how do I find acceleration from a velocity versus time graph? Well, acceleration is the value of the slope. So I'm looking at the value of the slope. How steep is the line? So now let's come back to our problem. So if I'm looking at steepness, the most forward acceleration is going to be the most positive acceleration, or positive slope. Most backward acceleration is going to be the most negative slope. So the steepest slope that is positive is object A with that steepness. So A is the most steep. The only other positive slope I see is D, but I can clearly see that D is shallower than A, so it is less. C has a backwards acceleration, so that's negative, and B has 0 slope or 0 acceleration. So B would become next, and C would be the next, or the least, or the most backward acceleration. So again here, we rank these by most positive to most negative slope. Now for displacement, what does our sheet say about displacement? Well, again, looking at my reference sheet, I'm looking at velocity versus time. How do I find displacement? Displacement is the area between the graph and x-axis. So remember that above the x-axis is positive, below the x-axis is negative. So let's look at that. Let's quickly talk about the areas. I won't tell you how we found these. I'll just talk through them quickly. The area of A. We've got this negative triangle down here. That negative triangle has an area of -10, 1/2 base times height. This positive triangle has a +10 area. So what's the total displacement for A? Well, displacement here would be 0 meters. What about B? You've got one rectangle. The area of this rectangle is a +40, so your displacement here is a +40 meters. Let's see. We've got this positive triangle in C. That's a +5. This triangle would be -5 if I do 1/2 base times height. So those displacements are both, or it's also 0 when I add those together. And then object D, you've got this one triangle. It's negative. So I've got an area of -20. So the displacement is -20 meters. So the most forward displacement is the most positive. That's 40. I don't need to write that. I need to write B. Then A and C are equal, being 0. And the only negative or backward displacement is D. So that's how those rankings would go. So now, let's move on. We've got 6 position time graphs and 6 velocity time graphs, and I want to put them in the table down here and then talk about the acceleration. So first description, this object is moving forward with a constant velocity. Well, to move forward, it needs to move in an upwards direction, so it must be one of these graphs, 1, 3, or 4. Now I want a constant velocity, so I don't want my steepness to change. That has to be graph 3, and we can also see that from our reference sheet. Now I want the object to move backwards, so that's either 2, 5, or 6. And I want it to be constant velocity. So again, it needs to be straight, so that would be graph 5. An object is moving forward and speeding up, so it must be sloping upward. Speeding up means getting steeper, so that's graph 1. Object moving backward needs to be sloping downward. If it's speeding up, it's getting steeper. That would be graph 2. Moving forward and slowing down, that means the graph is sloping upward, but the steepness is decreasing or it's getting shallower. That's graph 4. And then by default, the last one is graph 6, and that one does show moving backward, which is downward sloping, and slowing down means getting shallower. So how do these relate to velocity versus time graphs? So moving forward on a velocity graph means I'm above the x-axis. So that's either C, E, or F. Constant velocity means my velocity is not changing. So the graph that shows velocity not changing is E. Now the object is moving backward, so below, so either A, B, or D. Constant velocity means it's not changing. That must be graph B. Moving forward and speeding up, that's above the x-axis. Speeding up means it has to move away from 0. Those numbers are going to get larger. That is going to be graph F. Moving backward and speeding up means I'm below the x-axis, and again, I want my numbers to get further away from 0. That is graph A. If the object is moving forward and slowing down, that's above the x-axis. I want the numbers to get closer to 0, so that's C. And then by default, backward and slowing down must be graph D, and I can see that because it's below the x-axis, and that graph is getting closer and closer to 0. So now acceleration. It's either positive 0 or negative. So let's look at our velocity versus time graphs to help us with this, because acceleration, as we learned in the last little exercise, was the slope of velocity. So for graph E, what's the slope of this line? Well, the slope of that line is 0. Constant velocity, there is no acceleration. Graph B, same thing, slope is 0, so there is no acceleration. What about graph F? That line has a positive slope, so that must mean there's a positive acceleration. Graph A is sloping downward. That's a negative slope or negative acceleration. C is sloping downward, so that's a negative acceleration. D is sloping upward. That's a positive acceleration. So now let's come down here to our 6 statements. Well, to answer these, I kind of need all of my statements in view. Let's do the first 3 first. So, when acceleration is positive, what's a general rule I can know about the position graph? Well, my positive accelerations are graph 1 and graph 6. So what's common about those? One's getting steeper, one's getting shallower, one's increasing, one's decreasing. Well, if I think of these as opening one way or another, both of these graphs, if they were a cave, would open upward. So if you can think of these graphs as opening upward, if you took your hand and you made the shape of the graph, your hand would open up. That is a positive acceleration. That must mean that a negative acceleration is probably going to open downward. My negative accelerations are 2 and 4. So if I look at those do open downward. If I made my hand trace that graph, my hand would open downward. When the acceleration is 0, that's 3 and 5. I don't have to do anything opening upward or downward. The position graph is a straight line. So what about my velocity graph? Now acceleration is the slope of velocity, so I just have to talk about what is the slope doing. When the acceleration is positive, the velocity graph slopes up. If it's negative, the velocity graph slopes down or decreases. And when the acceleration is 0, the velocity graph is a horizontal line because the slope of that line would be 0. All right, so the top of this page really tests our ability to differentiate between a position graph and a velocity graph. So first, we are given a position graph. So I'm only looking at the top row of my reference sheet chart. Those velocity graph and acceleration graph things, I'm ignoring for this first one. So I have this, if you're in trigonometry or pre-calculus, this looks like a sine curve, but that doesn't matter. At what time does the object go the fastest forward? So when an object is moving forward on a position graph, that means it's sloping upward in a positive direction. How do I know when it's going the fastest? Well, the fastest means it's going the steepest. So what's the steepest part of this graph that slopes upward? Well, I see a pretty steep upward slope here and a pretty steep upward slope there. So this could be either 0 or 4 seconds because they look about the same steepness to me. So what about the second one? When is it going the fastest backwards? Well, when is it the steepest sloping this way? Well, the steepest sloping that way, it looks like it's at that point. That would be 2 seconds. At what time does the object have 0 velocity? Well, that would be anywhere where the velocity goes from positive to negative or negative to positive. Or I can think about any section or any spot where the graph flattens out to a slope of 0. So that would be 1 second and 3 seconds. So during what interval of time does the object have positive acceleration? Well, on the first part of this page, we came up with some rules. If the position graph opens upward, that means it has a positive acceleration. That's between 2 and 4 seconds. If it opens downward, it has a negative acceleration. That's between 0 and 2 seconds. So now let's move on to velocity. So now we got velocity graphs. At what times does this object go the fastest forward? Well, being forward means I have to be above the x-axis. So that's going to be either 0 or 1 seconds. So where is it going the fastest? 0 seconds or 1 second? Well, at 0, my velocity is way up here. At 1 second, my velocity is 0. So it's actually going the fastest forward at the very beginning at 0 seconds. When is it going the fastest backward? Well, if it's going backward, it has to be below the x-axis. What is my highest speed below the x-axis? Well, that's when it's furthest away, and that is at 2 seconds. At what times does the object have 0 velocity? Well, that's when my velocity graph is at 0. That would be here at 1 second and here at 4 seconds. During what interval of time does the object have positive acceleration? Acceleration for a velocity graph, I'm looking at the slope. The slope is positive between 2 and 4 seconds. During what interval of time does the object have negative acceleration? Well, negative acceleration on a velocity graph means negative slope. That's between 0 and 2 seconds. Now let's move on. Now we're going to draw some velocity graphs. Draw a solid line for the motion of the black object and a dotted line for the motion of the white object. So let's do that now. A white ball is dropped from rest at the top of a building. At the same time, a black ball is thrown upward with an initial speed of 30 meters per second. Use g, this means acceleration of gravity. How do I know it's an acceleration? Because the units are meters per second squared. So this is going to be the slope of my graph. Well, let's think about this. If I drop a white ball from rest, and this is my acceleration, upward's positive. If I drop a white ball, my velocities are going to be negative because it's going to be moving downward. So I'm going to take this 10, and every second, what this means is you're going to subtract 10 meters per second every second. So the white ball will have a graph that looks like that. The slope of that line is negative 10. And what that means is you add negative 10 meters per second every single second. That's what gravity does. A black ball is thrown upward with an initial speed of 30, which is right here. Now, the acceleration is the same for both because they're both under the influence of gravity. We haven't talked about gravity yet, but it says use this for your acceleration at negative 10. So the acceleration should be the same, meaning my slope should be the same, meaning the slope of that line is negative 10 also. So those are my two graphs for the white and the black ball. Now, over here on the right, a white car travels forward with a constant speed of 20 meters per second. At time t equals 0, a black car begins to accelerate from rest with an acceleration of 5 meters per second squared. So let's do the white car first. It's traveling forward with a constant speed of 20. Well, 20 is right here. That means the white car is just going a steady 20 meters per second. The black car is beginning from rest and has an acceleration of 5 meters per second squared. So that means every single second, it's gaining 5 meters per second. So the slope of this line should be 5, because that is my acceleration, and this is a velocity graph. So I can see the white car is traveling at a constant velocity, it's not changing, and every second the black car is adding 5 meters per second to its speed, because that's what acceleration is. So now down here we got a black car starting from rest, travels forward, speeding up to 30 meters per second in 3 seconds. So in 3 seconds, the black car speeds up to 30 meters per second, then travels with a constant velocity. So then the velocity stays the same and flattens out. At the same time, a white car starting from rest travels backward, speeding up to 20 meters per second in 2 seconds. So it speeds up to 20 in 2, and then travels with that constant velocity. That would be the graph for those 2 cars. And then finally down here in the bottom right, a white car initially traveling forward with a speed of 20 meters per second stops by having an acceleration of negative 10 meters per second squared. So the white car initially has a speed of 20. What this means is every second I subtract 10. So 1 second later, I subtract 10. Another second later, I subtract 10. So the white car is able to stop in 2 seconds. A black car initially traveling forward with a speed of 10 meters per second stops by having an acceleration of negative 2. So every second, I subtract 2 from its speed. That means by the time it reaches 5 seconds, if I have subtracted 2 every single second, it will have reached a speed of 0. The slope of this line should be negative 2. The slope of this line for the white car should be negative 10. I'll go ahead and warn you on this page, when we get down to the position graph, it's going to be very tedious and look like a lot of work. And just know that if you understand the concept of how we're getting the position from the velocity graph, that is enough. Because the entire test is multiple choice, you're not going to have to do nearly as much work for any of those questions as we're about to do for this. So first, an object moves so that it has a velocity versus time graph as shown. Change this representation into the object's acceleration, and then change the velocity versus time graph into the object's position versus time, assuming the object begins at 2 meters. And then we're going to draw a motion map showing the object's position and arrows representing velocity every 2 seconds. So the easiest thing first, acceleration. Acceleration is the slope of the velocity graph. I see there are 3 sections. There are 3 different slopes. There should be 3 separate sections to my acceleration graph. So what's the slope of the first section? Well, the first section is this one. That section has a rise of 8 and a run of also 8, so the slope there is 1 meter per second squared. So the slope is 1 for 8 seconds, because that's how long that section lasts. So a horizontal line at 1. This second section, it goes from 8 to negative 8, which is a rise of negative 16. How long did that take? Well, it went from 8 seconds to 16 seconds, so that was a run of 8. So the slope here is negative 2 meters per second squared, and that is the slope from 8 to 16 seconds. So I'll make that last at negative 2 from 8 to 16. Then finally, this last little section here from 16 to 20, the rise here is 0, the run is 4. That's a slope of 0 meters per second squared. That speed or velocity is not changing. All right, like I said, that's the easy part. Now let's go to position. It says that my position begins at 2 meters. So that's nice. I'll start my position at 2. So how can I tell how far it's gone after 5 seconds? Well, let's go back up to our graph up here. If I want to know what's the displacement or how far it's traveled in the first 5 seconds, I need to take the area within the first 5 seconds. Now, I could sit here and do this for every single second, and that would give me a very accurate depiction of this motion, but in the interest of time, because I don't want this video to be super, super long, it's already going to be long enough, I'm just going to do it every 5 seconds, and we'll go from there. Or I'll do it, we'll see. Okay, so the rise, or the height here, looks like to be not 7, looks like it's 5. The run here is 5. So calculating the area now, that's 1/2. 1/2 times 5 times 5, which would be 12.5. So what this means is from the beginning to 5 seconds, it has moved 12.5 meters. Well, if it was already at 2, it started at 2, and it went to the right 12.5. Where did it end up? Well, at 5 seconds, it would have to be at 14.5, which is right there. Now I'm going to choose another point. Let's choose, I don't know, let's say 8. So what's the area of this whole triangle from the beginning to 8? Let's get rid of that. All right, what's the area of that whole thing? Well, the base is 8 here, and the height is 8, so 1/2 times 8 times 8 would be 32 meters. But again, that is how far it is from its initial position after 8 seconds. So after 8 seconds, if it started at 2, move 32 meters to the right, then it should be at 34 meters, and that is at 8 seconds. So now let's choose another point. Let's choose 12 seconds. I'm choosing 12 because that's the moment it stops moving to the right. How do I know that? Because the graph goes negative afterwards. So let's take the area of this whole triangle from 0 to 12 seconds. So now the base of this triangle is 12. The height is 8. So what's 1/2 times 12 times 8? That would be 48 meters. So after 12 seconds, it's 48 meters to the right of where it started. So if it started at 2, that means at 12 seconds, it has gotten to 50. So there we go. So then what does it do? Now anything after this is negative. Let's do this area here, because I see it's a nice triangle. So we're going all the way out to 16 seconds here. So this whole area up here is 48. So now anything we do now takes away from that 48. Now we're going to be going back to the left and taking away from that position. So what's the area of this triangle? Well, the base here is 4. The height is -8. So what's 1/2 times 4 times -8? Well, that would be a -16. So now if I was at 50 here, my position was 50. Where am I now that I went to the left 16 meters? Well, now I would be at 34. So now at 16 seconds, we are back at 34, which is right there. And then let's go all the way to 20. So at this point, my position is 34 meters. So now how far back did this section from 16 to 20 get me? Well, the base here is 4. The height is -8. So the area of this whole triangle, the whole rectangle, square, whatever, is -32. So if I was at 34, I went to the left 32 meters, where did I end up? Well, I ended up back where I started, at 2 meters. So now what should it look like in between here? Well, from 0 to 8 seconds, this object was speeding up. If it's speeding up, that means your line should be getting steeper on your position graph. So from 0 to 8 seconds, my line, if I can do this somewhat correctly, should be getting steeper and steeper throughout those entire 8 seconds. What about after 8? Well, from 8 to 12, from here to here, this section of the graph slopes downward, but it's still above the x-axis. So that section means I'm moving to the right, but now I'm slowing down. If I'm moving to the right and slowing down, that should be getting shallower on a position graph. So this section should be getting shallower until it gets to 12 seconds, and now it starts turning around. From 12 to 16 seconds, that section represents moving to the left because it's below. The graph is getting away from the x-axis, away from 0, so that means it's speeding up. So what does it look like on a position graph when I'm moving to the left and speeding up? Well, I'm sloping downward but getting steeper. And then what does this last section mean up here? Constant negative velocity means I should have a straight line that is negative because I'm moving to the left, so I'm still sloping downward. So it should be a straight line from here to here. So what I'm going to go back and do now is draw this curve, hopefully, to where it can still show it speeding up, but then it ends up being straight. Somewhat straight there. That's what that position graph would look like. And again, that is way more than you're being asked to do in this test, but if we understand the different parts of this, how it shows moving right speeding up, moving right slowing down, moving left speeding up, moving left constant speed, then we're going to be good. Honestly, for the interest of time, this motion map down here doesn't really even matter, so I'm just going to skip it, if that's okay. All right, next here we have a position versus time graph representing the motion of a fish. The detector pointing north part, that just means that north is positive, and so it's moving in a positive direction, and I can see that because the graph initially is sloping upward. So A, how far from its starting point did the fish end up after the 10 seconds shown in the graph? How far from its starting point is a fancy way of asking for what's the displacement. So if the fish starts at 10 meters and ends up at 50 meters, then how far from its starting point did it end up? It was 40 meters away. And my justification can be I'm calculating the displacement, which is final minus initial position, which is 50 minus 10, or 40 meters. All right, so B, at the 3-second mark, which way is the fish moving? Well, at the 3-second mark, which is right here, that graph is sloping upward. And on a position graph, direction of motion comes from the direction of your slope. Since that's sloping upward, we can say that's moving in a positive direction, which in this case is north. My justification, graph slopes upward, which means a positive direction, which for this problem is north. So at the 5-second mark, is the fish moving faster than at 3, slower, or the same speed? So let's look at 5. At 5 seconds, the graph is like right there. So how does the slope here compare to the slope at 3? Well, I can see from the line I just drew, that slope there is steeper than at 3, and a steeper slope means that it must be moving faster because it has a steeper slope. Describe what the fish is doing at the 8-second mark. Well, 8 seconds is right here. So what happens when the graph goes from slowing down to the right and speeding up to the left? What happens in between that? Well, the slope of the line here is 0. Anytime the graph turns around on a position graph, that means it had to stop at some point. So any maximum or minimum of this graph, it changed directions. You can also say it stopped for a second. And justification, the graph went from sloping upward to sloping downward, so that must indicate a change in direction. So now we move on to the next problem. Instead of a position graph, we have a velocity graph, and we have the velocity graph of 2 joggers. So we have jogger A, which is this line, and jogger B, which is this line. So, first question, which jogger got a head start? Our initial thought is to say, okay, B starts ahead of A on the graph, so it must have gotten a head start. But hold the phone. What is this graph of? This graph is a velocity. So what does it mean that B's line starts above A's? All that means is that B is starting with a higher velocity than A. I don't know if B is way over here and A is over here, or if they're right next to each other. I don't know where they are. Velocity graph can't tell me position. So we have no idea actually who got a head start because I can't get position from a velocity graph. That's our justification. So, part B, describe the similarities and differences between the motion of the 2 joggers. Well, the similarity is they're both above the x-axis, which on a velocity graph means they're both moving to the right, if this is moving right and left. They are both speeding up. And how do I know that? Because both these graphs are moving away from the x-axis. A difference could be A speeds up faster than B, which means it has a greater acceleration than B because the line is steeper, so it's gaining speed at a faster rate. And those are really the main similarities and differences that I can think of. They're moving in the same direction, they're both speeding up, but A is speeding up faster than B is because the line is steeper, and this is a velocity graph. So what was happening with the joggers at point X? Point X is this point here where the lines intersect. On a position graph, that would mean that they were at the same position, and so they were right beside each other, but on a velocity graph, all that means is that both joggers have the same velocity. So they're moving at the same rate. I still don't know where they are, though. I would have to have more information given to me in the problem to figure out exactly where they are and if they are in the same spot at that moment. All I can tell from the graph, because it is a velocity graph, is that they have the same velocity because they have the same y value at that point. So now we're on to our last 2 pages. They're very similar. They all are in this style. They give you a graph, and they ask the same 3 questions. Is the cart moving at the very beginning? Is it speeding up, slowing down, or constant speed? And which way is the cart moving? So this is a great way to practice using our reference sheet for graphs, determining what about a position graph tells me these three things, what about a velocity graph tells me these three things, and seeing if we can get that from our reference sheet in preparation for our test on Friday. Okay, first, I have two position versus time graphs. Just by looking at this shape, if I find that on my reference sheet, this is moving to the right and slowing down. It's moving to the right because it's in general sloping upward. It's slowing down because that line is getting less steep. So I'm going to be lazy. I'm going to say it slows down. It's moving to the right, or it could be up, depending on the problem. So then the question I have now is, at the very beginning, is the cart moving? Well, to slow down, I have to already have been moving. And if I look at the slope of the graph to begin with, because slope tells me velocity, there is a slope in the beginning. It's sloping upward. So the answer here would be yes, it is, because the graph is sloped to start with. Same thing with the second graph. There's a slope at the beginning here, which means there is a velocity, so this cart would also be moving. If I look at my reference sheet for this shape of a graph, I see that this graph is moving left because it's sloping downward. Left, it also could be down. And I know it's also slowing down because it's getting less steep. So what about my velocity graphs? How do I tell if it's moving in the beginning on a velocity graph? Well, velocity tells me straight up if it's moving or not. If my velocity is 0, it's not moving. If it's not 0, it is. This initial velocity here is not 0. So yes, that cart is moving. The velocity graph slopes downward. It slopes towards 0. So these numbers, my velocity values, are getting smaller and smaller. That means it's slowing down. And the graph is above the x-axis, so it must be moving in a positive direction, which is right or up. So this velocity graph starts at a value not 0. So yes, that's moving at the beginning. It's sloping away from 0, so these velocity values are increasing. So it's speeding up. Which way does the cart move? It's above the x-axis, so in a positive direction. All right, home stretch, last page. This velocity graph, it didn't copy very well, should go all the way to 0 here. So since my initial velocity value is 0, it is not moving to start. What does happen? After the beginning, it slopes upward away from 0. My velocity values get larger, so it's speeding up. It's above the x-axis, so it moves in a positive direction. Now we're back to position graphs, so I have to switch my thinking. This is the exact same as the first one on the last page, so I know it's slowing down, it's getting shallower. It's sloped upward, so it's moving in a positive direction. And it is moving at the beginning because the line is sloped to start with. Two more. Velocity graph. My velocity is not 0 to start, so it is moving, but I know it's moving in a negative direction because it is below the x-axis, and the line is sloping towards 0. So yes, the line's increasing, but my numbers on my velocity, the magnitudes are getting smaller because they're getting closer to 0, so that must be slowing down. And then finally, another position graph. If I look at this graph on my reference sheet, that matches something that is moving left because it's sloping downward. It could be left or down. So it's moving in a negative direction. And it is also speeding up because the graph is getting steeper from left to right. So at the very beginning, is the cart moving? Well, I ask myself, does the slope have a value in the beginning? In the beginning, the slope of the line looks like this. So the slope of that line would be 0. The line starts flat out at the beginning and then gets steeper in the negative direction. So that cart was not moving initially because the slope at the very beginning would be 0. So that indicates no velocity, no motion.